So we've now seen a few linear data structures, and in this video we're going to move on to nonlinear data structures, and that is trees. So a tree will store elements hierarchically. A tree is a set of nodes. At each node we store the object that we're working with, and every node has a parent and any number of children. Now we have a few particularly defined nodes in this tree, and you may also hear me refer to nodes as vertices as well. These are equivalent. Vertices comes from the standpoint of a tree being a particular type of graph, which is my area, and we're going to get to graphs later in this course, and nodes are usually more specific to tree, but nodes and vertices are the same thing. So we have a few particularly defined nodes. We have the root node, so every rooted tree, what we're considering here, every tree has exactly one root, and that is the node that has no parents, the only node with no parents. We also have internal nodes, and here we've got the following internal nodes. So these are nodes which have at least one child. And then everything else is an external node. So external nodes are those nodes which have no children. And these are also called leaves sometimes. Now, the depth of a node is defined as how many edges we have to go through in order to reach the root. So for example, the depth of sales is 1 because we go through this one edge to reach the root. Whereas, is 1. Whereas the depth of Canada, for example, is 3 because we go through these 3 edges in order to reach the root, and the depth of desktops is 1. The height of a tree is just the maximum depth. So if we assigned a depth to all of these nodes, we take whatever the maximum one is, and that's the height of our tree. So for example, the height of this tree is 3, and this is realized by any one of these 3 external nodes here. So trees have a lot of different applications, particularly in storing data which has a hierarchical structure, such as organizational charts or file systems where we have a directory, and inside that we have subdirectories, which also have subdirectories in other files, or programming environments. Again, you have a solution which has a project, and inside that project you have folders which have files, etc. So there are several things we can do with a tree. So all of these are position-based operations, so we're given the node that we're working with. So with root, this is returning the position, returning the node, which is the root. So again, how we would call this on a tree, because you may not have worked with a tree before, you've probably worked with stacks and queues and lists before, but again, if we have a tree T, if we want to call any of these operations, this is just our tree dot whatever the operation is. So for example, root. Okay. So the name of our structure, so we have some tree and it's called T, dot, and then the method call. Now parent will take a position and return whatever the parent node is. There's only one parent. Children will take a position, take a node, and return the list of all children that that node has. Is internal and is external will just return true or false based on if that node is external. This will return true if it has at least one child. Is external will return true if it has no children. And is root will just check to see, is this node P the root of our entire tree, the only one that has no parents. Okay, and we always have size and is empty. Again, this is just how many nodes do we have and do we have no nodes. And then we have separately elements, which will give us the list of all items that we have stored in our tree, or we could get a list of all positions, which is the list of nodes. So nodes store elements. And given 2 positions, just swapping the elements which are stored at those positions, or given a position and an object, here we're just replacing whatever we had stored at this position with this new object. So we have a few different methods, and we have additional update methods that we could define by the data structure implementing the tree ADT. Now with the other linear structures that we've seen, we already had a method to traverse it. So a traversal is just a way of visiting every element systematically. For the linear structures we saw, it was easier to see that we could just, start at one end, maybe the beginning of a list, and then work our way all the way to the end of the list. But given the complex structure of trees, we have a few different ways in which they can be traversed. So again, traversing this is just accessing or visiting all nodes of this tree. And when I say visit, this is just an operation in which we're saying that we encountered that node. So this could be anything. This could be maybe we print the node, whatever is stored at it, or maybe we're comparing that node to some value. If we're looking for, the letter J, for example, this is how we would look through the tree to find that letter J. So visit could be many things, but for us right now, we're just considering that this is the order in which we encounter a node is based on when we visit it. Now, all traversals recursively traverse from the top root node to children nodes. And the only difference between these two traversals here is whether you visit a node before the recursive calls to its children or after the recursive calls to its children. So let's see an example here of, let's do the pre-order traversal on this tree here. So let's say we start with our root node, and I'm going to draw this so that I'm going to circle the node when we visit it, and just so that you can see when we visit it and when we're recurring on children. So we start with A, and with pre-order traversal we visit it first, before we recur on children. So now we recur on children, we get to B, we visit it, and then we go to our children and visit them. And E has no children, so we exit that recursive call. B still has other children that it can recur on. Now we work our way back to A is the only one left that has children left to visit. So we get to C, we visit it, and after we visit it, we recur on its children. So we visit G, and then H, and then I. So now we're done with all children of C. How we got here was from A. A still has children left. So now we visit D, and we come back up and A has no other children. So this was that order when I circled. This is the order we would encounter those following a pre-order traversal. So now let's do a post-order traversal. This is that we visit after we recur on children. So starting with A, so this isn't visiting yet. Because A has children, we're going to recur on its children first. So we go now to B. We haven't visited B yet. B has children, so we go to its children first. So now we're at E. E has no children, so now we visit it. Go back up to B. B still has children left, so we recur on F. F has no children, so we visit F. Then we go back up to B. We've already recurred on all children, so now only after we've done that do we visit B. We go back up to A. A still has children left, so we go down to its other child, C, which also has children, so we go down to its children. And we can now visit G, and then H, and then I. Now we can visit C, because we've already visited all of its children. And then we work our way back over to D. And now that we've visited all of A's children, we can finally visit A. So A gets visited last. Notice. So this is the order in which we visit nodes with a post-order traversal. Now, both of these traversals take total linear time, big O of n. So this is the worst case running time of calling pre-order on the root, which as a result, we ultimately call pre-order on every single node in our tree. So the total cost of this entire function is big O of n. And I know there's some recursive calls in here, but if you think about this from the standpoint of we call pre-order from here, we call pre-order exactly once for each node, and we have n nodes. And during that call, the non-recursive overhead we have is constant. So we can charge for visiting here and for each child. So each node gets charged once for itself and once for all children. So as a result, each node ends up getting charged twice, once for itself, and then once it also gets charged when we're at its parent. So our total running time is linear. So which traversal would you want to use? The only difference is in whether you would want to visit a node before a recursive call to children or after. So for example, preorder would be particularly useful when you need to print linear ordering of documents. For example, say we had here an introduction, and then here is chapter 1, chapter 2, etc. We would want to print this in order, our intro before chapter 1, 2, and 3. Post order, this can be used in order to determine, for example, the amount of space that a directory uses. So we have, if we want to figure out how much space this directory is using, first we have to figure out how much space this directory is using, and in order to do that, we have to figure out how much space this file and this file is using. We add those together to get the space of this. Then once we have the space of all of these directories, will that give us the space of how much memory our root directory is using. Okay. There's also a particular kind of tree called a binary tree. Now, when I say binary tree for this course, I always mean a full binary tree. So binary tree, kind of without this, just means that every node has at most 2 children. So that means it could be 0, 1, or 2 children. When we have full here, this means that 1 is not an option. Every node has either 0 children or 2 children. We can always enforce that this is the case by adding external nodes in order to guarantee that every internal node has exactly 2 children, and that'll actually make implementing some other data structures that use a binary tree easier. So it'll reduce how much we have to handle those kind of odd edge cases. So we can already always assume that we're working with a full binary tree, meaning that if a node has children, it has exactly 2 of them. And moreover, its children are ordered, so we have each one that has a child has a left child and a right child. There's another way that we could define this recursively, which is that in the base case, just a single node here is a binary tree. So this is our one root node. And we can also build up more complex binary trees using, here is a binary tree on the left. So this is just an abstract tree with some many items here, and a binary tree on the right, which has a root, and we connect them by one root. So this is the left subtree of this node, of the root node, and this is the right subtree of this root node. So this entire thing then is a binary tree. So this is a recursive definition of binary trees. This will be particularly helpful for us to use when we're looking at some of the properties that binary trees have. There's a lot of applications of these. So for example, we can use them to represent an expression. So we have here that the internal nodes are operators and the external nodes are operands. So we've got the expression 2 times a minus 1, all of that plus the result of 3 times b. So this maps nicely here because we have that our operators are binary. They have a left and a right side. We could also use this to model a decision tree. So we've got that our internal nodes are questions that are either yes or no, true or false. And then as a result of those, we have at the bottom our external nodes, the leaves, which are decisions. So after asking so many questions, we come to some conclusion, some decision. Now, binary trees, because they have at most 2 children, they have a lot of really nice properties, and these are important because we're going to use these later in order to argue about the running time of algorithms that work on binary trees, and we have a lot of them that do that. So here I have n is the number of nodes that we've got, e is the number of external nodes. Remember, external nodes have no children. I is the number of internal nodes. These are the ones that have at least 1 child. And h is the height of our tree, which is the maximum depth. So for example, the height of this tree is 2, and the height of this tree on the right is 3. Now I didn't put this down, but just because of the way of how we defined an internal and external node, every node is either internal or external. So the total number of nodes we have is E plus I. Now all of these properties are important for us. However, I consider some of them to be more important, particularly important. And that is because if we know these ones in red, then from them we can derive the other ones just by using substitution and our other formulas. So these ones in red I think are the most important ones. And because of that, let's go ahead and prove these 3. They don't have very long proofs. So let's show that this is true. And we're going to use structural induction in order to do that. So remember what the recursive definition of a binary tree is. So let me clear this out. We're going to show that this is true with structural induction. So we've got, this is what we want to show. The number of external nodes is equal to the number of internal nodes plus 1. And we want to say that this is true for any possible binary tree that we could come up with. So in order to do this, we're going to use structural induction. And what that means is we're going to use the recursive definition that we had for binary trees. And remember what that is. Here we've got, in the base case, this is our definition again, that just a single node is a binary tree. So just as a reminder here, so BT just means binary tree. And in our recursive case, we could take a binary tree here on the left. So as long as this is a binary tree and this is a binary tree, then we could use them to construct another even larger binary tree. So this entire thing here is a binary tree. So we're going to use this definition, this recursive definition, in order to prove by induction that this equality holds for every possible binary tree. Okay, so what that means, how do we prove by induction? So this is just a reminder for us. We have to show that this property holds for our base case. And as it turns out, it does. So this is true for our base case. And why this is true? Well, let's see. We have only one node here, and it has no children. So that means that the number of external nodes that we have, the ones that have no children, is 1, and the number of internal nodes that we have is 0. So we're okay, at least in this base case. Now we have to show that this is true using our recursive case. So how we do that is we're going to assume already that this property is true for this, just this left binary tree and this right binary tree, and then use that to show that it's true for this entire larger binary tree that we construct. So in order to kind of separate them, to show which one I'm talking about, I'm going to write it this way. So we're going to assume that this property, what we want to show, is true for everything. We're going to assume that this does hold already for the left subtree. So that means that the number of external nodes, let's write it this way, in our left subtree is equal to the number of internal nodes that we've got in our left subtree, plus 1. And also for our right subtree. So the number of external nodes in our right subtree is equal to the number of internal nodes in our right subtree, plus 1. So we're going to start off by assuming that this is true. Something we can use is the definition of what it means for something to be internal or external. So for example, we know that the number of external nodes in this entire tree, so let's call this T, this entire thing here, including the left, right one, and this root. We know that the number of external nodes in it, that whole tree, we can write this with respect to the left and right tree. So external is a node that has no children. Note that this root node does have children, so that's not contributing to that number. So however many external nodes we have in this entire thing is based on how many we have in the left subtree plus however many we have in the right subtree. So we can use this later. And we can do the same thing for internal nodes. Remember, internal is it has at least one child. So we have some internal nodes in our left tree, we have some internal nodes in our right tree, and we also added this root node, which is also internal because it has children. So we have that the number of internal nodes in this larger tree T is equal to however many we had in the right tree, in the left tree, we've still got them. However many we have in the right tree, we've still got those too. And we just added one with the root. Okay, so now we just have to substitute here. So this means that however many external nodes we have in our entire tree is equal to, now I'm going to use, we have however many nodes are in our left tree here, plus however many are in our right tree here. But already I'm going to substitute, we're assuming, okay, we're already assuming that however many are in our is I number of internal nodes of our left tree plus 1, and then that however many are in our right tree are also I r plus 1. Now let's combine these. We have however many internal nodes in our left tree plus 1 plus however many internal nodes are in our right tree. We have a formula for that already. This is however many internal nodes are in our entire tree. That's this part here. And then we have 1 left over. So we're finished with this proof. Okay, so that finally completes that the number of external nodes equals the number of internal nodes plus 1. So we are done with this one. Now to show this one. This is actually much easier. The height can be no more than however many internal nodes we have, and in fact this tree gives that upper bound here. So look at this one here. We've got 3 internal nodes here, here, and here, and the height of our tree is 3. This is the distance from our external node going through all of those internal nodes until it reaches the root. So this is an example of that upper bound, that our height can't possibly be more than however many internal nodes we have, because in the worst case our height is realized by a path which goes through all of those internal nodes. Okay, and lastly, let's go ahead and prove this one, and we're going to use structural induction again in order to do this. So let's clear this out. We want to show that the number of external nodes we have is no more than 2 to the power of the height of our tree. And remember, height is maximum depth. So I'm not going to write the recursive definition of a binary tree again, but let's prove again by induction, by structural induction. And start off by showing that this is true for the base case. So that means when we have just one single node, this is our entire binary tree. Well, in that case, we know that E, which is the number of external nodes, is equal to 1, because this has no children. And the height of this tree is equal to 0, because the distance from this node to itself is 0. It doesn't have to go through any edges. So we're okay, because in this case we've got 2 to the power of 0 is equal to 1. So this inequality holds just for our base case at least. So now we have to show that this is also true for, let's call this our inductive step. So we're going to start off by assuming this is true for the left tree and the right tree. So again, let's distinguish that by showing that the number of external nodes in our left tree is less than or equal to 2 to the power of the height of our left tree, and that the same is true except for our right tree. So the number of external nodes in our right tree is less than or equal to 2 to the power of the height of our right tree. And maybe it would be nice to draw this here just so we can see this to refer to. So this is our left tree, this is our right tree, maybe one of them is taller than the other one, and they're joined by this node. Okay, so this is that entire tree that we're working with, T. We want to show, assuming this holds for our left tree and our right tree, that it holds for everything. So, let's see, we know that if we were to take just the number of external nodes we have total, this is again using what we had before, that this is just however many external nodes we have in our left tree plus our right tree, because when we include that root node, we're not adding any additional external nodes because it has children. And now we're going to substitute what we had already assumed, those inequalities, for how many external nodes are in our left tree and in our right tree. So this is based on our inductive hypothesis. This is less than or equal to 2 times the height of our left tree, plus, substituting again here, 2 times the height of our right tree. Now, we're not sure which one of these is larger. Maybe our left tree is larger or our right tree is larger in terms of height, but we know that no matter which one is larger, if we take whichever one of them is larger, this entire sum is no more than if we were to take the largest one. Let's say the left one is the largest, so the height of the left is the largest, then this is the larger value compared to this one. So this sum would be no more than this value plus that same value again instead of the smaller one. So that's 2 times whatever that larger value is. So 2 times whichever one of these values is larger. So that's 2 to the power of, we don't know if it's the height of L or R, so we just have to take whichever one of them is larger. So we're going to take the maximum here. Maximum between the height of L and the height of R. Now we have this is equal to 2 to the power of, again, maximum between the height of L and the height of R. Plus 1. Why plus 1? Because we have this 2 here, so they have a common base. And now we finally have this top part here, the exponent. This is exactly the height of our original tree, because the height of our tree with respect to the left and the right side, no matter which one of these is larger, maybe the left is the maximum or the right is the maximum with respect to the height, but we added 1 extra edge to the height of that because we added this root node. So now this is equal to 2 to the power of the height of our tree. So this completes our inductive proof. So we are done here. QED. So nice practice also for structural induction moving forward. Okay, so we finished with this proof. Oops. Again, the others which you see in black, you can obtain them by substituting in or using algebra, taking the logarithm of either sides in order to get that. So for example, you could get from here to the next one just by taking the logarithm of both sides. And the other ones are quite similar to that as well. Alright, so we will use these later in order to argue about the runtime of an algorithm that runs on a binary tree. Okay, now a couple last things. Binary trees, because they have exactly 2 children, we can define for them a separate traversal called in-order traversal. So this is just that the same kind of traversal as what we saw before with pre-order and post-order. Remember, pre-order we were visiting before we recurred on any of its children, and post-order we had visited after we had recurred on children. But with in-order, we're visiting right in between, after we recur on the left child, but before we recur on the right child. So let's see how this would work for this tree. So if we start with the root A, we recur on the left side. So we get to B, we recur on the left side, we get to D. D has no left child, so now we visit D. And D has no right child, so we're finished with that call. We go back up to B, we visit it. It has a right child, so we go down to E, which has a left child, so we go to H. We visit H, come back up to E, visit E, go down to I, visit it. Now we can go, we've already gone through everything in the left subtree of A, so now we can visit A, go down to C, visit its left child F, visit C, and then finally visit G. So this is that order in which we encountered vertices. So again, in-order traversal also runs in total linear time. We visit each node exactly once. And we can use this, we could specialize this in order to print a fully parenthesized infix notation of the arithmetic expression tree from earlier. This is just before we recur on the left side, we print a starting left parentheses, and then after we recur on the right side, we print a closing right parentheses. So this gives us that infix notation, fully parenthesized, for the arithmetic expression tree from a couple slides earlier. Now, all of the tree traversal algorithms we've seen so far are forms of iterators. This is just a systematic way of visiting each node exactly once. And we can unify them into a single design pattern by relaxing the requirement that each node be visited exactly once. And the resulting traversal method is called the Euler-Tor traversal. So the advantage of this is it allows us to, it allows for more general kinds of algorithms to be expressed easily, because it has embedded in it pre-order, post-order, and in-order traversals as special cases. So the idea is that we visit something from, we have a call where we visit from the left, we visit from below, and we visit from the right. So 3 different calls to visit. And when we visit is, we visit from the left prior to recursively calling on children. We visit from below after we've recurred on the left, but before we recur on the right. And we visit from the right after we have recurred on all children. So this is a kind of a combination of all 3 of those traversals. So you can imagine this as, if we want to do an Euler-Tor traversal of this tree, this is literally, we start at the top and we work our way kind of drawing immediately around the perimeter of this tree. And when we encounter a node, here we've encountered this node from the left first, and then we work our way down. Then we encounter the x from the left, we encounter 2 from the left, then 2 from below, then 2 from the right, then x from below, minus from the left, 5 from the left, below, right, minus from below, 1 from the left, below, and right, minus from the right, and so forth. This continues this way, right? Now, if we were to only print out these values when we encounter them from the left, this would give us the prefix notation for this arithmetic expression. If we only print out values when we encounter them from below, this is the same as in-order traversal, this is the infix notation. And if we only printed out values when we encounter them on the right, this is the postfix notation. This is how we would encounter them along the post-order traversal. So this simplifies a little bit how to find prefix, infix, and postfix, another problem I think from your CS2 class. Alright, now finally, how would we actually implement a tree? There's a few different ways. One is by using a linked data structure. I know this looks really complicated, but internally this isn't quite so bad. But this is that we have every node stores 3 things. So this node stores the element, the actual object which we're keeping track of, and then we also have the parent node and children nodes. So B is the root, it has no parent, so this is the only one that has a null parent node. And then we store a reference to all of its children. So here we've got a sequence for each child. So here, this points to its child A, D, and F. Those are those children, A, D, and F here. A, for example, its parent goes back to B, and it has no children. D, its parent again goes back to B, and it has 3 children, so its last pointer here goes to a sequence of its children nodes. Here we have C, its parent points back to D, and it has no children, and also E points back to D, and it has no children. So if we use this, all of the tree operations that we had discussed run in constant time using this implementation, with the exception of listing out all children. So this runs in time proportional to however many children there are. And if we, of course, list out all elements or all positions, this will run in linear time based on how many items we have. Okay, but the amount of space we use is proportional to however many nodes we have, is linear with respect to that. So there's another way that we could implement this a little bit simplified if we know that we're working with a binary tree. And in that case, each node stores its parent, whatever element we're storing at that position, left child, and a right child. So our root node is the only one which has no parent, but every other node has here a reference back to its parent. So A's parent is B. A has no left child, it has no right child, and we're storing that element A here, for example. So again, this is linear time, big O of n storage, constant time for nearly all tree operations. For example, the only ones that this is the exception to is getting a list of all elements or positions is linear time. Now for binary trees, we can list all children in constant time because there are exactly 2 of them, and that's a constant number of children. Now there's one other way that we can implement binary trees specifically, not any arbitrary tree, but just for binary trees, and that is using an array. So we'll store nodes at specific indices based on where they occur in our tree. So notice that we're not using rank 0 at all, we just start with rank 1. And we always store the root node at rank 1, and then for every other node we store where it's at in the array based on the rank of its parent. So for example, the left child will have rank 2 times whatever its parent is. So A is the left child of B. It gets rank 2 because that number is equal to 2 times the rank of its parent 1. For right children, their rank will be based on 2 times whatever the parent is plus 1. So D's rank is 3. C, for example, since it's the left child of D, we just get 2 times the rank of D, which is 6. That's exactly where we store C. And for E, we take 2 times the rank of its parent plus 1, which is what gives us 7. So again, with this implementation, we can implement, with this structure, we can implement all operations for a tree in constant time, the only exception being getting all elements or getting all positions are linear time. However, the downside of this representation is how much space it uses. So on the previous slide, the amount of space this implementation uses is linear. Depends on how many items we have. But if we're using this implementation, we throw everything into an array, so it's based on the size of the array, but how many spaces do we have to keep in this array in order to store all elements? Because you'll notice that some spots here are blank. We're not using them at all. And in the worst case, we have a tree that's extremely lopsided, one that looks like this. Let's say every right node has a child, and it continues this way, right? So this is an example of a binary tree. In this case, here we have this last node will have a rank of 2 times its parent, and this one has plus 1, and this one has a rank of 2 times its parent plus 1. And essentially what we'll need is a total number of spaces proportional to 2 times whatever the height of our tree is in big O notation. So this is the height of our tree, h, how many edges we'd have to go up. But unfortunately, we know from one of the previous slides that our height could be as large as however many internal nodes we have. Right? And in this case, where we have these are all of our internal nodes, and only one external node corresponding to each internal node plus 1. This can be as large as 2 to the nth power, where n is the number of items that we have. So this is huge. This is exponential. This is incredibly bad in terms of memory. Now, there are a few instances where we can say, okay, this case where it's very lopsided and gives us this bad space complexity, where we can at least guarantee that that doesn't happen, and we'll see a few instances of that. But otherwise, in general, this would be a bad representation for binary trees if we can't say anything more about our tree data structure. Okay, so as always, if you have any questions, please let me know. Post on Piazza. See you in the next video.